So welcome everybody. Thanks for coming today to Rails School. We're going to talk about the traveling salesperson problem here in a few minutes. Before we do that, I'm going to introduce Rails School for those of you that don't know, and for the video, I'm going to introduce myself, and then I'm going to ask you all to introduce yourselves. And I'm going to share my desktop so that folks online can see the notes easily. Cool. So Rails School, I started almost 4 years ago here in San Francisco. It sort of took the reins of a prior Ruby class here at Noisebridge called Star Monkeys. And I think from the Poignant Guide to Ruby.
Why?
Yeah, they appeared. There are characters that appeared there. And I sort of engineered it not to die the death that the Star Monkeys group died. I wanted this class to go on forever. And to that end, I made it a little bit loose, the requirements for students to show up or for teachers to teach. And the name of the game is being sustainable and fun and sort of distinguished from other meetups around the city in that we're sort of disciplined and focused. There's no greasy food on our keyboards. Everybody that shows up is here to focus and sort of collaborate in person to learn programming subjects. And that's sort of the role that I see the class filling. We've definitely expanded beyond Ruby and Rails. We do everything web and things not web. For example, we had a guest speaker teach us all PowerShell, right? Which is, raise your hand if you're familiar with PowerShell. It's basically, it's Microsoft's new shell to improve on cmd.exe. Like they're trying to compete with Unix land.
Yeah,
and
not recently, right?
I've had it for a couple of years, but it's evolving.
Yeah.
And the key innovation is that it's fundamentally object driven. It's basically a wrapper, from my understanding, on the Common Language Runtime and .NET and C#. So when you, for example, pipe things on the command line, you're piping objects, structured data rather than text in Unix. It's a cool mind experiment, and it was a really fun class. To give an example of how unorthodox we are here at Rails School at Noisebridge. Today, we're not going to do anything Railsy, but we will use Ruby, which is characteristic of us. We really love Ruby here, and I think it'll be a lot of fun. My name's Gabe. I started the class about 4 years ago, almost 4 years ago. Next week will be our 4th anniversary. And I got into web software out of school about 6 years ago, wound up writing a lot of Rails, got a little bit disenchanted with Rails, but along the way found that I really did enjoy Ruby very much. And what I'm excited about these days for writing web software would be Elixir and Phoenix, because you can do concurrent programming, and the sort of immutable functional paradigm is amusing to me and useful. And this traveling salesman idea, well, that's weird looking. Weird. Oops. Okay. It's a little glitch in my browser. The traveling salesperson problem is a really well-known problem because it, why is it well-known? Well, it's easy to explain, and it maps, it's a well-known problem in a certain category of problems. Does anybody know what category of problems it's well-known in?
Optimization, I guess.
Sure. Let me ask you, can you, for large graphs of the traveling salesman, let's define the traveling salesman problem. It's given a bunch of cities with coordinates, come up with the shortest path where you can visit all the cities. Is that right? So the idea is you have a salesman that has to travel to many cities on his or her route, a salesperson, and you want to compute the fastest route. Is this strictly something that you can compute for all inputs?
Yeah, I think so.
It's actually really hard. Yes, yeah, the answer is yes, but sometimes it could take more amount of time than there are more seconds than there are particles in the universe, for example, if you have enough cities. So that's why it's a really fun problem. It's NP something or other. It may be NP complete. And it's gonna be really fun to, that's why it's sort of fun to solve, because you can't just set out to write a script to solve this in Ruby. You can for small graphs, but it falls apart pretty quickly. NP hard. And towards the end, we'll discuss the difference between NP hard and NP complete. But first, I'd like to do intros. So I introduce myself. I do a lot of web software. And I'd like to just go starting with you. Doesn't have to be anything fancy. Just what's your background as far as programming, and what are you hoping to learn today? And also, if you were to join us in future classes. Also, I don't know if the three of you have been here before. Raise your hand if you have. You're all new? Awesome. So I'll take sort of little notes here. We can do this pretty quickly, but I am interested in what you're hoping to accomplish today, as well as generally, because we want to cater to you to keep you in the community and keep you coming.
I'm Ben. I'm mostly a Python programmer, but I've been through the Ruby tutorials, just like the basic 101 kind of thing on the Ruby website, and liked it, but just haven't really put as much use yet.
Cool. So in case it wasn't clear, you come to whatever lessons you want to. Sometimes we'll do cumulative ones, but you don't strictly have to come to the sequence. Just drop in. If you create an account on our website, we'll email you once a week with the lesson. We meet once a week, 7 to 9 here at Noisebridge. By the way, we love Noisebridge. They don't ask anything from us, so we try to throw them money. On our FAQ, you can find out how to donate, and there's a box to donate behind me. They really prefer, their favorite kind of donation is a recurring donation, even as little as $5 or $10 a month, because it helps them plan their budget during the course of the year, which can be challenging at like this neo-anarchist collective we are inhabiting. Cool. Thanks, Ben. And you?
I'm Rob.
Rob?
Yeah. And I started out with Python too, and then Ruby at the same time, and realized they're the same exact time. I just spent more time. I do a lot of web applications, and I use Rails. And I like it. It was very painful to learn, but now that I have them, so.
Rails was painful to learn.
Yeah, it's just so MVC and so, put in these niches, these little nooks that you have to know about afterwards. Just like, you don't know it after one day, you know it after that.
Sure. Another part of the problem what I've seen, because I got into it long enough to remember when it wasn't as complicated as it is, it's that we programmers just automate and automate and automate. And every little pain point we automate, which creates layers of tooling on top of tooling. And it just becomes a learning curve to learn, like, why is there Rails this and Rake that and Bundler and Gem and the asset pipeline. These are just complexities that serve a purpose for the professionals that invented them. But when you try and get started with them, it's really rough.
Do you know the answer to that, legend, why do you use Rake versus Rails? Because they said, no, you've probably heard Rails 5, they're making it all Rails. Do you know why Rake was used? Yeah, I don't know. It's like,
I don't know. Yeah, I don't know. That'd be a curious thing to investigate in another class. So they're fixing it a little bit. We're definitely grateful for a lot of those things, like Bundler and the asset pipeline have inspired other package managers and other builds, front-end build systems. But yeah, it's intimidating at first. And I don't even know how intimidating it is, because when I started, Bundler was just invented, so everybody was learning it. The asset pipeline didn't exist. What else? Mostly those two things.
Plugin systems. It was oh yeah, you mentioned Monday.
Yeah.
I started after 2.3, was merging, we were moving from 2.3 to 3.
Yep.
And it was just so hellish, because like I had to look at 2, right? Because I was like, oh, I'm going to job next week in this field, but oh no, right there. Okay.
That sounds rough.
And then, and luckily it didn't happen that way, and I was doing most IT work, so I had time and everything. And then, yeah, it was really a huge jump going from 2 to 3. It was like nothing was the same. Your code had no hope, and you had hours and hours of migration time to put into it. 3 to 4 was a lot better. I think 4 and 5 should be cool.
Rails has gotten better. I do like it, but the learning curve is not diminished, which is tough for outreach organizations because we are sort of an outreach organization. We don't charge any money. We try to be visible around the Noise Bridge community, like, hey, come hack with us. It's tough to say, Rails isn't that hard. It's good for beginners because it's not really true. It's like a professional tool.
Hello, my name is Farouk. I'm the last person on the list. You can see it. Farouk, F-A-R-R-U-H. So I'm pretty new to programming. I've been learning Ruby and Rails for 3 months, and I've built some like 4 to 5 small web applications for Ruby and Rails, and now I'm trying to learn more algorithms because where I'm really lacking some knowledge. So yeah, that's pretty much about it.
Cool, thank you. So this is the right class for you, for sure.
Yeah.
And algorithms, I would treat, well, first of all, they unfortunately, for better or worse, you do need to learn them for jobs, but also you should see them as something sort of fun, as little puzzles, sort of a hobby type thing. And Traveling Salesman is a good one. It's a meaty one to jump into, right? But we are standing on the shoulders of giants. This guide that I'm going to follow was invented by a very smart person named Peter Norvig. I don't remember his bio, but he's a pretty impressive dude. He's an AI wizard who worked with NASA and Sun, and now he teaches. Oh, he works at Google, but I also think he's a researcher, a researcher and a teacher. Super smart guy, right? So sometimes these really smart people are kind of generous, and he just in his free time or his 20% time, he publishes these IPython notebooks that we can follow to learn the traveling salesman problem without our heads exploding. I've skimmed it a couple times, and it's pretty amazing work that he's done here. And it's long because he's very gentle with us. He introduces the complexity over time. So even if we only get halfway through, or even a third of the way through, we will have learned some concepts and have had fun. So we're ready to go. So that's awesome. And nobody has joined us online, so we're good. All right, thanks, Ben, Rob, and Farouk. Okay, so without getting into the computational theory stuff, because they don't typically ask that in interviews. NP complete is like a good thing to be literate about, which we can talk about more at the end. But rest assured that it's a way of categorizing different problems into buckets of how much time they would take to complete, or how much memory they would take to complete, or whether or not other problems map to those problems, or vice versa. So this theory stuff, you don't have to focus on. But the actual algorithms, the work that we're going to be doing with this algorithms approach will carry over into sort of the type of algorithms questions people ask in interviews, tech challenges for sure.
So right now I'm going around more balls.
So
And what is this city called? So here and here, I'm just going.
So cool. So when you start doing the problem, the easiest thing for a mortal programmer to do is just try every possible route and compute the total distance of each route and sort the results by total distance, right? Which you can do for a few cities, but because you have the number of cities minus 1 factorial, and factorial gets very large possibilities, even with only 10 cities, we have 181,000 possibilities to test. So that seems doable. I see all of you have like pretty recent computers. You could probably test that, but every city you add adds another order of magnitude, and you will fall over pretty soon. And it actually guides us. This Wikipedia article is great. Exact solutions to the problem exist. Like the brute force solution is exact. If you try every path and sort by the distance, the minimum distance path is the minimum distance path. You have found the perfect solution. We'll see that Peter Norvig will take us on a journey through starting with brute force, through adding various levels of clever ideas towards trying fewer possibilities. And according to this Wikipedia article, by using the exact techniques, we can get to 40 to 60 cities. So that tells me is greater than 60 cities. We just don't know. You can't answer it with the computers that we have in a reasonable amount of human scale time. And then you have to use non-exact solutions, right? So they're calling that heuristic here. It means you get a solution that's very good, right? Probably good enough for a salesman to go on his way or her way, but not exact. We can't prove that this is the best solution. In fact, it's very likely not the best, but it's very close to the best. Does that make sense? Cool. So in the description, I linked also to a Stack Overflow answer for how to draw SVGs in Ruby. And by the way, I think what I'm going to do here is create a Git repo and sort of push very rapidly to it, because I want to move pretty fast. I want to move faster than you could necessarily copy and paste, or I could paste into the buffer and you could copy it, or you could type. So I think that's what I'm going to go ahead and do. I'm going to start that now. And let's see. Raise your hand if you're familiar with Git. Like a little bit of Git trivia. If I do that, it complains that there's nothing to commit. Does anybody know how to force it to let me commit?
How about is allow empty gonna work?
That was what I was going to try.
Oh,
Thank Dash M has. Yeah, allow empty is good if like you're screwing around. I just want to test or if you just want to create a repo that's empty. It's nice to be familiar with that. Otherwise, you think that it's not possible. Did I add the origin? I didn't add the origin.
I can install Hub, by the way.
Have you ever installed?
Hub, HTTP.
I've not. Does it allow you to do that?
It has a view Hub. And Hub create.
Oh, to create, yeah, that makes sense. I just don't create repos that often.
Oh,
You know, how often do you? Like,
Well,
Cool. All right, so we got ourselves a repo, and I'll go ahead. I pushed it. All right, cool. I'll go ahead and paste this in our group buffer. By the way, I haven't explained this, but oh, thought I got it. I haven't explained how we try to use our website, but one of the little features of our website is that we have this embedded buffer. It's just an iframe running Etherpad, and it's handy for taking notes, taking shared notes like a Google Doc, because you can paste links so that if you have a useful link that you want to paste, you can share it with the class very easily. You can also share code snippets. So in order to access this, you have to create an account and log in and click Show Whiteboard. And that's how we get your email addresses. Oh, I pasted the wrong link. Rails School TSP. Okay. So let's just start from the top of the tutorial. And here we go. As I said earlier, the problem is defined as given a set of cities. Cities have coordinates. And cities don't have coordinates. That would be implied. You could derive the distances from the coordinates, but given a set of cities with distances between each city, so you can think of like an old like road atlas. Do you remember that page like at the beginning? That's like, you know, it's X miles from Atlanta to DC. Yeah. So I think that's the analogy I like to use for this input. For the pairs of cities, you have their distances. Find a tour of the cities with a minimum total distance. A tour means you start at one city, visit every other city exactly once, and then return to the starting city. Sounds simple, right? This is a well-known intractable problem, meaning there are no efficient solutions that work for a large number of cities. But we can create an inefficient algorithm that works fine for a small number of cities, about a dozen. You can also find a nearly shortest tour. That would be like the heuristic or inexact answer that for over thousands of cities. Actually, the fact there is no efficient algorithm is liberating. It means that we can use a very simple, inefficient algorithm and not feel too bad about it. In this exercise, we will look at some algorithms for solving the problem. The most important lesson is how to think about solving a problem like this. The details of this particular problem are less important. That's a really great attitude to have because the work we do today could actually carry over into our solving many other kinds of problems. Let's first think about the vocabulary of this problem. What are the important concepts, and are we sure we understand them well enough to implement the concepts as data or functions? This is really key because in computer science, this falls under the like general umbrella of computer science. Some of these words actually have precise meanings, and it's super kind of Peter to like explain them to us and not assume that we know what they are. We'll start to consider impossible implementations in Python, but won't make definitive choices yet. So that is why this class is going to be sort of interesting, is because we're going to have to map the Python to Ruby, and we'll probably uncover interesting learnings in doing so. A city is atomic in the sense that we don't have to know anything about the components or attributes of the city. We don't need to know its name, populations, or anything else, except that we do have to know how far it is from other cities. So a city is basically a unique symbol and we have a table of the distances between these unique symbols. We need to represent a set of cities. Python's set data type might be appropriate for that. It's unclear to me at this point why a simple array why a set is preferred over a simple array. If we do have to use a set, Ruby has sets also. It's no problem. Does anybody know? Can we define a set?
It's like an array, except it enforces uniqueness.
Awesome. And what are like some things that we often do with sets?
Map.
What are the really simple math operations that you associate with sets?
Oh, like joining sets together or testing to see if things are members of the set.
Testing if something's in a set, joining them together would typically be a union, where you wind up with a valid set that has all the elements. So if they're duplicates, it accounts for that. We also like to do an intersection where we find the elements that appear in both sets, and sometimes we do exclusive or. We find items that exist in exactly one of the two sets. So that's handy fundamental stuff to be familiar with. Distance, we will need to know the distance between two cities. If A and B are cities, this can be done with a function distance A or B, or with a dict, distance A, B. What's a dict in Ruby typically? We don't have dicts in Ruby. What do we use instead?
Like an array?
A hash. Yeah. I think, yeah, that'll do for us. Cool. A tour is an ordered list of cities. So a list or tuple data types would work. In our case, I think array really suits that very well. Ruby's got dynamic arrays that are sort of the best of both worlds. So it serves a really good purpose when you need a list. Total distance for a tour is the sum of the distances of adjacent cities in a tour. So we'll probably have a function total distance of tour. We're going to skip over the IPython stuff. IPython is pretty neat because it's basically like my impression of it. I'm not an expert, but it's like a document, like a piece of text that has executable code inside of it. So it's like a combination, like Word document and a spreadsheet but instead of Visual Basic and Excel, you have Python. Okay, so let us do algorithm 1, try all tours. And he gives these handy method names to keep unique methods. Our first algorithm, which finds the tour with shortest total distance with a straightforward approach. Generate all the possible tours of the cities and choose the shortest one. The tour with the minimum total distance. We can implement this as a function exact. And Ruby doesn't have functions, we call them methods, but it's good enough, the same thing for this purpose. Exact TSP. Here's the design philosophy we'll use. We'll just write code that closely mirrors the English description of the problem. This will require some auxiliary functions and data structures. Just assume that we'll be able to define them as well using the same design philosophy. So he creates a method, exact TSP cities, that returns the shortest of all tours of cities. And shortest returns the min of tours by total distance. So we're going to gloss over the Python stuff, but I'll be able to translate it into Ruby, and you just ask questions if you're curious. A tour starts in one city and then visits each of the other cities in order before finally returning to the start. A natural representation of the set of available cities is a Python set. A natural representation of a tour is a sequence that is a permutation of the set. Below, we list the 6 possible tours permutations of a set of 3 cities. The tuple 1, 2, 3, for example, represents a tour that starts in city 1, moves to 2, then 3, then returns to 1 to finish the tour. And Peter considered adding the origin city again at the end, but declined. So let's go with his idea. So as an example, we get all the permutations of the paths, and then we get a list of the permutations of the cities. Now for the notion of distance, we define total distance tour as the sum of the distances between consecutive cities in the tour. That part is shown below. It is easy. We'll deal with that in a minute. He actually decides to use XY coordinates. Maybe that's where I got the idea because I had skimmed it earlier. let's do it his way, because that seems more useful in real life, right? It's sort of skipping having to create that table from the road atlas, and instead you can get that distance from an API or from a geospatial database. Okay. So I'm going to start just hacking away here. We're going to have a city class. It takes an XY coordinate. It's up to you. You may get more out of it if you build it too. And then what you can do is like pull in my repo and CP back and forth if you get behind. Does that make sense? I am going to push because I do want to move fast. I don't want you to count on typing, but I also want you to try things also. So a city can have an X and a Y value. And we can define a class method called distance that just returns that's crazy. City equal complex. That's wild. Let's see if Ruby has such a thing. That's wild. Cool. Well, let's just do assign an instance variable complex equals complex of X and Y, and self.distance city A, city B. We can just, according to Peter Norvig, we can take the absolute value of A minus B. That's pretty crazy if this works.
I'm guessing we don't have an area in mind that you're looking to get into.
So we can use pry and require our city.rb just for now. And we can have a city.new, say 5 at 5. B is city.new, say 1010. City.distance A comma B. Oh, I just forgot Ruby absolute value. That's the easiest way to do that. Oh, it's a method on the number. Ode forces you to reload the class. You can do gem install pry. And I already have it installed. And then once you have pry installed, you can do pry-r, the file you want to require. Sure, that is a macro that defines a getter. Does that make sense?
Yeah.
That's what allows us to call city.a.complex and city B dot complex, it maps to, it creates a getter that just reads from that instance variable. So but we're already learning something new. Like, I'm already glad I showed up today because of this super maintainable hack that Peter has introduced to us, which is if you want the distance between things with coordinates, you can use complex numbers and subtract the complex, so you don't have to do city A dot x minus city B dot x squared plus city A dot y minus city B dot y squared, the whole thing under a square root, right? He's just saving us from typing some code. Super cool. I'm going to go ahead and add that and push it. I'll also do I'll add the pry to the gem file, because if we want to use another gem, let's be generous with the libraries that we use. Let's not try to reinvent things. I'll add a gem file with pry. Cool. Questions so far? All right. Here's how to make a set of random cities. So this seems like something that we can define as a class method on city, maybe. And in Ruby, it'd be something like this. Yeah. Let me know if you have any questions. Otherwise, I'll just sort of assume that you've seen stuff like this before. City.new, and he is saying for x 10 to 890 rand range. I wonder if Ruby has a sugar for that, or if we have to do it ourselves. Yeah, I think we have to do it ourselves. So so rand 880 plus 10. Is that the same thing? I think that's how we have to do it in Ruby. This stuff doesn't really matter, does it? Does anybody have a sense of why he chose those magic numbers? I don't know. Well, here we go. Rand gives us random on 0 to the value you pass to it, and we're adding 10 to I think get what he's got. New seed. we can call strand. So let's make sure, well, if we just want to be really sure, we can just put that in here. That just calls a method that seeds the random number generator so that we get different results every time. I think later on he's going to benchmark it, and you get more accurate benchmarking if you get different inputs. Okay, so here he's using destructured assignment, which we can do in Ruby 2 to quickly have some variables. So at this point, I'm going to go ahead and create a new Ruby file. I'm just going to call it main.rb because that's where our sort of the body of our script is going to go. And here I'm going to require city.rb. And here I'm going to put Saran because I think it makes more sense. We might want random numbers other places.
I think students at the whiteboard, I think the function that you can run in Ruby to get a random number between 1 and 100 say.
Nice. I like it. Yeah, that's much prettier looking.
Okay.
So so it's 10 to 890, right? That's why Ruby doesn't need that weird function. It's just like the most unsurprising, awesome API. Thank you. Cool. So we use destructured assignment here. We can just do like 8, 10, 100, 1,000 each map and city.random cities n. Does that make sense? Does anybody have any questions?
But like it usually doesn't
Yeah, so this actually isn't going to work really unless we do something like this, binding.pry. And then we just write Ruby main.rb and require pry. The locals aren't available when it's required because they don't leak outside of the file scope. So here's another technique that'll drop us into a pry instance in the right place, but with those locals available to play with. Sweet. Cool. So is everybody convinced that this sort of works? Cool. I'll go ahead and commit it. City dot random cities and main.rb. Cool. All right. What do we have next from Peter? All right, now we are ready to apply the exact TSP function to find the minimal tour through the set of cities. So let's do, let's start copying. tour equal exact TSP cities 8, puts tour, puts total distance, total distance. And then we have to, oh, so that works because he already wrote the methods above. We sort of skimmed through, so now we have to translate them to Ruby. So I'm just going to copy total distance, and then we'll sort of translate it to Ruby line by line. So def total distance tour. So let's see, how would we do this? We would use like range 0 to tour dot length. Reduce.
I think most instances where that thing would be used, probably not, because like both devices would be hard.
0. We're going to sum this up. Do sum and
I think
I.
got simple, it would just mess it up if there were like more.
It's a little bit weird because usually we would use the city itself rather than I. Usually we iterate over the cities, but I just want to be very brain dead and copy and paste his code. So so sum plus equal sum plus city dot distance tour sub I tour sub I minus 1. So I think that's basically it. We're zipping from 0 to tour length and reducing into 0, which is what he does for I in range, except I think might be.
No. I had
Let's try it.
It's got this like.
All tours equals city, all tours. So we need to create all tours. Shortest all tours, yeah. So we need to just copy his stuff and translate it into Ruby. Not a big deal. At this point, a tour will be a list and a distance. So I go ahead and suggest we create a class that captures that. So a class that captures that would be something like this. Class tour, definitionalize, cities, distance. So basically a value class. I'm just going to do it the simplest way. But we could, if I were doing this in real Ruby, I might inherit from OpenStruct or something. like a nice pattern to get a value object. We'll use the adder reader again. Initialize adder reader on both of these cities and distance. And then we can do this kind of shorthand, tours.min by distance. Then we just need all tours. Okay. So in Python, it was able to call it's pretty un-Ruby-ish, but we can do the same thing. Ruby.
Can we change the function names so they're a little more Ruby and more coherent?
Definitely. So in Ruby, we can just call permutation on the array. So cities permutation each do permutation. City city.new tour.new. Permutation and so we can actually calculate the distance right here. Much more Ruby-ish. Def distance and and I'm just going to replace tour with cities. We don't need total distance. That was kind of weird. You know, he's doing it in this very awesome hacky way. It's like all one big script. But let's write Ruby code like we'd expect Ruby code to look. This might actually work. Does anybody have a comment on this distance method? Anything that looks scary about it? The scariest thing that I see here is at line 4, we're referencing the city class by its constant name, which is kind of sketchy. It's sketchy from like a maintenance point of view. Like we're saying that the tour class has to know that the city class exists, which is not elegant, but I'm cool with it for now. Does anybody see any errors? Or can we go ahead and
can we put an underscore between all tours and that function definition? It's just killing me.
Yeah, totally. I like the curly braces when we return something. So underscore here, and this is very strange to see in Ruby. Typically it would look like that, right?
Yeah.
So puts tour dot cities. Puts tour dot distance. This is looking pretty good to me, truthfully. I'm sure we have syntax errors. But let's go ahead and run it. Uninitialized constant tour. I just forgot to require it. It's a spelling error. I think it's city.length -1. Cool. I think if we override toString for city. And set it to like complex.2s, you can eyeball this more easily. Okay. I just want to spot check our method because we changed it a little bit. Puts summing distance between cities I and cities I -1. And that'll see that our loop is correct. Oh. Yeah, I forgot that we did that. 614, 384. Because we have to go back to the beginning, but it appears first. 614 and 793, 859 and 793, 730 and 859, 695 and 730, 660 and 695, 456 and 660, 384 and 456. Looks good to me. Cool. So let's see what Peter does next. Let me push for y'all. What did we call this? Exact TSP works. And let's bear with him, and we'll get to graphing the cities in a minute, right? Let's wait to graph them till he starts graphing them. But I think I'm looking forward to graphing them because it'll be nice to visualize it. So we saw when all that output was spitting out that we were doing the same something over and over again. So maybe there is a way to not do as much work to get the same result. So we did algorithm 1.0, and that was to go over every last permutation. But some permutations are the same. Right? If you have cities 1, 2, 3, there are 6 permutations, but those aren't 6 separate tours, right? You could do it clockwise or counterclockwise, right? So if we can cut out half the tours right off the bat, we should do it. So we can make our TSP program faster. Wow. This is really unfortunate, folks. But like the whatever language she's using to do the math equations, like MathJax or LaTeX or something, got screwed up by the Internet Archive, I think, which stinks. I don't know why he took this off his website, by the way. It's very frustrating because this is such a useful guide. That's going to be frustrating this whole time. The fact that we can't see his equations here. Oh, it is working. Raise your hand if it's working. Are you able to see these?
Are you on Mac or are you using Mac?
Mac?
Oh, did you install the special math suite for?
No.
What are you on Safari?
Firefox.
I'm going to try a couple. What are you using for your browser?
I'm on Firefox.
Okay, it worked in Chrome, but not Chromium. So let's go ahead and, oh, it broke in front of me. It worked when I first loaded, and then it broke. Well, can I just ask you if we have questions?
Sure.
Cool. Okay. So it seems like he's just redefining all tours to chop off the first start and doing start for all the other cities.
I think you can right click it and choose show map as text command. That might help illustrate.
Right click these little guys?
Yeah.
Whoa!
Right? This is part of the Mac XML markup language that no one like ever used. And so if I just go into the system, no one cares. And then we got buddy application.
But I can't fix it for the whole document?
No.
I wonder if it's just like an old version of MathJax. But yeah, for if I want to find a single one, I can right click and see it. Thank you. All right, is everybody ready? Does anybody have any questions before we do our first optimization? Cool. So here in all tours, we're going to grab the first city. And then we'll do we'll permutate over cities minus start. You know what, for now, I'm actually just gonna set Sarand to 0 so we can compare our output, right? And when it comes to time to benchmark, we can set it back to random. Went and so I've got the new method in def new all tours. I'm just going to run our code with Sarand with the seed set to 0 and see that our distance was 2,249. And then I'm just going to rename this all tours, old all tours, and start with our new all tours. $2,249. So we changed our code and it didn't break the answer. So that sounds good to me. I'm just going to commit this as as algorithm 1.1. Remove redundant tours, duplicate tours. Cool. So he's claiming that this is going to make it as n times faster. Cool. I don't think this applies to us using lists instead of tuples. I think that's a Python thing. Cool. Now he plots. All right. Looking a long list of numbers is not very enlightening. If we could plot a tour, we'd understand it better. I define plot tour to apply a TSP algorithm to a set of cities, plot the resulting tour, and print information about the total distance. Okay. So here is where we look at this stuff. I do want to be more structured. I think this will pay for itself pretty fast. So let's use Nokogiri. Ruby doesn't have an XML parser or an XML generator included in the standard library. So Nokogiri is the gem that serves that purpose in Ruby. And we can go ahead and define a method on tour, tour.plot. Okay. And while we're building Nokogiri, we can copy some code. Oops. Okay. And at the top, we can require Nokogiri. Nokogiri is installed. This ViewBox stuff, -100, -100, 200, 200. I don't really feel that great about it. Let's see what he does. See, oh, he's using a library. We don't care about these ticks so much as long as our cities are printed out. So let's say we're from 0 to what were those 590, 800? So 0 to 900 on the X. Just guessing here. and 600 on the y. And we can do cities.each do xy. Cities.each do city. And I'm gonna put a finding.pry here because I don't remember. Puts cities, puts tour.cities. Here I'm just gonna do tour.plot. Run it. Define method plot tour lowercase tour the instance dot plot. So a city has a complex. And how do we get the x and y out of that? City complex. Shout out any ideas you have. City complex dot real, city complex imaginary. What a goofy idea. So real is the x and all right, so we're trying to draw some circles. Does that make sense? And how do we write this? I think we can call builder.2s. Nope. XML. Builder.2xml. All right. File. We'll just do file.write. .now.iso 8601. You do like file.write, the timestamp plus SVG. SVG. Builder.2xml. 377 bytes. And on a Mac, you can do just open. Oh my gosh, it worked. It's kind of ugly because it's on a transparent background. Let's go ahead and do see if Chromium fills in the background. Okay, we're plotting our cities. It's not as beautiful as Peter's plot. I did spend about 5 minutes Googling for a Ruby gem that would give us pretty plots like Peter's. I didn't find any.
I really like the it's in around those circles. This is good.
Cool. It should be good enough. We'll see. So those are the plots. And then we need to draw some lines, some paths. It's pretty wild stuff. I don't really feel like trying to figure out his API. I think we can figure this out ourselves. Basically, let's have some private methods like def, private, points. We'll call plot points doc here. Make sure it works. Chromium. Okay, it still works, and it's exactly the same. I'm just breaking it up into different methods so that we can not drive ourselves crazy. And then we'll have a method plot paths. And here, start by doing like something like cities.eachcons 2. So you get each consecutive pair of cities, I think. No, I just forgot the method. It's right next to each cons. Each slice. See how we're repeating? So each slice will do that make sense? We can pair off our array this way. What happens if we have an odd number? I think this will work. If we have an odd number, no. Turning my brain a little bit. Let's just play with it visually and see where it takes us. Is each slice 2. Oh, I did want each cons. That's why I was hurting my brain. I want each cons because we want to draw a path. Between each pair. 0 to 1, 1 to 2, 2 to 3, 3 to 5. I'm a dork. And we can shove the last one in there at the end. Does that look good? So we can do something like cities plus we're appending at the end cities dot first each cons 2 do A, B, right? And we do walk.path, I think. I'm not sure. Let's see what this guy says. Path. SVG path. This is really gross. We'll call this path data equals dot map join this is brutal. 100, each of these are points. Sometimes they're joined on L's, sometimes. So maybe we can just do one big path. Cities, map, AB, string, city, city.complex dot real, city complex dot imaginary, dot join on the string L and path data equal M space path data C talk dot path D equal D's path data and fill red, actually stroke red, stroke width 3. All right, let's see what happens. Didn't work at all because I forgot to call plot paths. Cool. So it's actually working. We just have to set the fill to none or something. That's pretty crazy. I'll push this up. Somebody should write a charting library for Ruby. SVG path fill none. Holy crap, it's pretty rad. So with so few cities, it's very boring. And we also know it's the exact solution, right? With lots of cities, you can tell by looking, just eyeballing these charts, how close it is to optimal. Because a crappy one will have lots of jigs and jags, whereas a good one will be like very smooth. It'll snake around in like to keep the path very short and visit lots of cities. I'm gonna push this because I would be surprised if anybody kept up with me. Whew. Okay. That's simple plotting working. I'm not going to bother to do all his fancy stuff because of how painful that was. You know, he gives you this stuff. That's pretty rad. I like it, but the important thing is to visualize. Let's try a much harder 10 city tour. I'm going over to main, and I'm just changing this line to cities 10. Looks good, right? You can just see with your eyes that it looks like a pretty decent tour. But it's starting to get slow, just at 10 cities. He wants things to be more beautiful. We don't. No, that was the other link. So with 24 cities, it would take 16 billion years. There must be a better way. So to find we have actually succeeded in finding in the fastest solution to the exact problem. But it's not a very exciting solution because it was pretty straightforward. We tried all of them. We realized there were duplicates. We got rid of duplicates. And now we can intuitively say that, like, in order to find the very fastest tour, we have to look at every tour. And that's going to take forever. So where it gets really fun is exact algorithms. But so as long as if we're willing to settle for something reasonably short, that's not necessarily the shortest, then we can scale to many cities. Any questions? Cool.
Is our algorithm designed such that we can supply if there's like 3, 4, 5 and watch how it takes long?
Can we get to that?
What?
Can we get to that? That's a great idea. We should do that. We should have like a framework for benchmarking it and so forth. But I want to get to an interesting algorithm because what we've seen so far hasn't been super interesting. So this one I highly recommend you pay attention to because there's a wide variety of problems that can boil down to finding a path, right? The traveling salesman problem is related to the shortest path problem. Which is super useful for like Google Maps. And it is NP the traveling salesman problem is slightly different, but related to. Traveling salesman problem is even more difficult than the shortest path problem. So just take my word for it. If you go all the way through Peter Norvig's work, it'll set you up to solve shortest path better. And shortest path is a more reasonable thing to try and solve. And in fact, it can be solved in polynomial time. And the traveling salesman problem can't. I don't know how I wound up there. Let's see. Oh, the nearest neighbor algorithm is how we're going to start by solving traveling salesman. It's also used for solving shortest path, and that is it's very natural algorithm. From your point on the graph, pick the nearest neighbor, right? You can intuitively think of why this would be better than picking, say, a random neighbor, right? If the cities, there are cases where a random neighbor wouldn't be better if you set up the graph to be really awful. But if you think the graph is evenly distributed, which we know ours is because we picked random numbers on the plane, then you're not going to want to jump all over. You're not going to want to jump from New York to LA when you know that you have to visit Boston, right? So you're in New York, you say, all right, who is my nearest unvisited city? And you've got Boston, and that's closer than LA. You haven't visited either one of them. You have enough information to guess that your total tour will be shorter if you visit Boston rather than LA. Does that make sense? That's all you need to know. It's not more complicated than that. And it's something we can implement right now, right? So I'm just going to copy and paste, and then we can get down to it. Greedy TSP. So our tour starts with the start city. We set a set of unvisited that is cities minus start. We're just using simple arrays here because they may just be good enough. While unvisited dot any c equal nearest neighbor from tour minus one. That's the last city in the tour to in unvisited, we append C, and then remove unvisited from C. We remove C from unvisited. I think that's how you do it in Ruby. Honestly, I'm partial to using loop do and break break unless unvisited.any, and then return tor. Nearest neighbor A, comma cities. Oops. And we're just going to do cities.min by city. And this distance between that city and A. We have that. City.distance A, comma city. And all right, so I'm just going to do, I'm going to plot exact is that. I'm going to put exact.distance. And this plot build it business, I want to give us like a handy file name. File name equal now.2s. So I have an easier time. So we can actually plot both now. Puts exact.distance, or we can do something like this. Yeah, puts exact.distance, exact dot plot exact file name, so I can open exact.svg. And here we can just substitute exact with greedy. Okay. Append is not the right method. It's does anybody remember what it is? Push in Ruby, and it's unvisited.delete. I'm calling distance on array. This is because I'm not creating a tour. I need to tour.new. Tour. Cool. The exact distance was 2,200. Our greedy algorithm got us 2,600, and we can open up these SVGs. The exact one looks like this, and the greedy one is going to look not as good, right? So sort of smells that we could do better would be that we're crossing over ourselves. And just with your eyeball, you can see that that this is shorter, right? Unfortunately, fortunately, this greedy one will scale to many cities. So we could actually do, I'm gonna comment the exact stuff out and show you that we can scale to many cities now, where we knew that 24 cities would take millions of years. Now we can do 1,000 cities. And it should be pretty fast. I bet the slowest part was probably generating the SVG. Or that, we'll find out. Cool, so this is where it gets fun, folks. Basically, the premise is we're taking this super ugly graph and we just add little bits of clever ideas and make it more beautiful, right? So this is what the whole class was leading up to, is having something like this that we can iterate over. And if you're down over the next 10 or 15 minutes, we're going over a little bit, I'd like to improve it a little bit. Are you all game? Cool. So here's our starting point. Let's get rid of, let's make it better. So I'm skipping ahead. Can we do better? Can we find shorter tours without taking an exponentially increasing amount of time? The problem with our exact was it takes every city that you add is an exponentially larger time interval to calculate the exact tour. Our challenge is to combine the speed of the greedy algorithm with the precision of the exact algorithm. This is like the really fun part. Think of a number from 1 to n factorial. Here's an idea. The exact TSP algorithm is too slow for large n because it considers all n factorial tours. But the greedy TSP algorithm considers exactly one tour, the tour that starts at an arbitrary city and then transitions to the nearest neighbor repeatedly. Not a very smart algorithm. Could we get a good compromise between execution speed and total tour distance if we considered more than one but less than n factorial tours? What's a number between n factorial, 1 and n factorial, and how can we use that to create a new algorithm? Algorithm 3, greedy nearest neighbor from all starting points, right? So if we try nearest neighbor from every starting point, we're only adding the amount of time proportional to the number of cities. And we're trying a bunch of tours and some of them will be faster, right? So this isn't that complicated and we can get a better answer and it won't take forever. And I should push, I'm sorry, folks. Let's think how to improve the greedy algorithm. In the plot of the 100 city tour with greedy TSP, we see that there are a few very long edges between cities. These come out because we get to a certain point and we already deleted the closer cities from unvisited. So we have to make that hop to the next unvisited city, which might be all the way across the country. In a way, this just seems like bad luck. The way we flow from neighbor to neighbor just happens to leave a few very long edges. Just as with buying lottery tickets, we can improve our luck by trying more often. So that's the idea. For each city, run the greeting algorithm with that city as the starting point. Choose the resulting tour with the shortest distance. So with n cities, we run the greedy TSP algorithm n times, meaning the run will be n times longer, but the resulting tour will, in most cases, be shorter, and always at least as short as greedy TSP. It'll never be worse. To implement all greedy TSP, we just take the shortest tour over all starting cities. So we're reusing the same method we wrote for greedy TSP. We're just giving it the option of passing in a star city so that we can wrap this with all greedy. Cool. So we'll do greedy, and then we'll put all greedy. This should actually help a lot because our graph is quite large. Right, so we're basically trying 1,000 different ideas. Oops. And Python.
I don't think it does. Try to ask mine.
Shouldn't take that long.
That's like a new quotation mark and ask mine is switch.
Well, we're making my computer work. However fast this returned, it should only take 1,000 times that speed, right? It shouldn't be that slow. So maybe I'm doing something dumb here. It's kind of scary. There are certain things we could fix right away. I have a lot of memory on this computer. We could have a memo here that is equal to hash with a you memorize these distances because calculating the distance between cities, it's silly to do that over and over again. So way you can create a hash with a default value is like this. It's a pretty snazzy trick. And we can do key equal this, and it'll only run when there's no value. So we could do memo and pass in as the key to the hash an array of city A, comma city B, comma dot sort. Right? By sorting, we can make sure that A&B is the same as BA. It's kind of snazzy. And run that. Sort by what is it? Foo dot object ID. Right? We can sort by object ID. It's still kind of slow, huh? Let's see, where are we doing that? All greedy. Cities.map. Cities.each with index. Map city index puts index. So we can see how fast it's going. So it's moving, but pretty slow. If we do a much smaller n, then we'll have less of a bad time until we get to our more clever algorithms that are faster. So let's do cities 100. Look at the difference. That's a little bit faster. Where did I do that puts? Okay. So with 100 cities, by trying 100 different tours, we were able to bring our distance down from 6,700 to 6,300, right? And we can chromium greedy. Look at that, and then we can open all greedy. That should look better. So we have fewer crossed lines. It's starting to unravel. Pretty cool. Any questions? I'm going to push this. All right. Let's see if we can do a little bit better, and then let's go home and get some rest. Cool. I'm sorry, this is just really fun for me. Like, I usually like to close right at 9 because I want to go home too, but it's really fun. All right. Greedy nearest neighbor with exact end. Let's read it. Of the several very long edges between cities, it looks like most of them appear near the end of the tour, right? Because we have fewer nearest neighbors. We have fewest neighbors left that are candidates for our nearest neighbor. That makes sense. When there are only a few cities left, it's not surprising that the nearest one might be far away. Use the greedy algorithm for all but the last few cities, about 8, and then use the exact algorithm over all possible ways to complete the tour. I love this tutorial because he's not trying anything that we couldn't think of if we really brainstormed. You know, a lot of times you read about algorithms and it's like, how did anybody ever come up with that? None of us would have come up with it in a million years. So far, the things he's doing are like pretty sensible. Cool.
And that's when it got stuck. It's one of my, but it's definitely still on the UK keyboard right now. It's still on the UK keyboard right now. Yeah, because it's the at sign and the quotation marks are switched on the UK keyboard.
All right, so this is where it gets kind of weird. The first part was just the greedy, the greedy. Oh, we haven't combined yet. So he's even babying us because we know that this first part would be faster by doing the all greedy, but he's babying us and saying, let's start with greedy exact end without doing all greedy, and then we'll combine the two. So ends equal, where's our list? I wish I knew how Python worked. I think it's unvisited permutations. Permutations. dot entities
I'm gonna say it's not international. With us, oh, so says you pay English. Oh. I would say it's the more. Or is it just US English? Yeah, it's like the rest of the world.
This is crazy. Let's see. All right, it takes a lot of thought to do the translation. Thank you all for your patience. Please let me know if you see a bug. Um,
It was fine, it was pretty fine. And after I installed the solution, sort of kind of, it goes through all this and it gets to this point and it's trying to do up the desktop. And it's got the radio from here and it's got the prompt there. This stuff. I'm thinking. Probably five. Yeah.
But it actually worked. And it's in the middle. So translated it from Python. It worked. And I'm not comparing exact. I'm comparing greedy to all greedy to greedy exact end. So greedy exact end is where we carve out the last 8 and do the exact match on the last 8, and it came out in between. So we were able to bring it down from 6,700 from plain greedy to 6,500, but it's still not as good as all greedy. So I think before we go home, the last thing we should do, which is what I think he's going to do next, is combine those 2 optimizations and see if we can get it. We should be able to beat 6383. Does that sound good? And we can go ahead and Chromium this guy. Not too bad. So he's also doing the benchmarking of time for 100 cities, which we haven't done. But I trust that one reason that I don't want to do it is because I may have made mistakes, or the Ruby stuff might add time that makes everything look like it's the same, even though he was careful to make sure that everything's sort of optimized. But that's something that we can go back and do later. Greedy nearest neighbor with both ends. Ooh, a random one. This is awesome. He's just like winging it. He's like, what if we try a few of this and a little bit of that and see how it goes? So this is pretty exciting. I don't understand this Python code. Oh, min length of cities. So in Ruby, you get cities dot length, comma, start size, min, dot times cities dot sample. Are we going to get duplicates? we want to try 12 random cities. So my sampling is wrong, right? Ruby sample array without a replacement. I think sample array must take a parameter. Yeah. So we can just start equal cities.sample. And then we won't get the duplicates because sample takes care of it. Shortest of starts.map, start, greedy, exact end, TSP, cities, start, end size. I think it's just that simple. And then we add that at the bottom. I mean, TSPs here. It's like a joke, like computers are really good at automating stuff. So you type one command and you get 5 bugs. Okay, so we're still not as good, but maybe it's faster. So you're combining, he's picking and choosing which different things he wants to try and looking for the optimal. But we still haven't beat trying the greedy for every start city, which was expensive, which we saw when we did 1,000 cities. It was kind of expensive. But we can Chromium that this guy and see that it looks about the same, huh? Cool. So how far did we get? We got like almost 40% of the way through this article. And I think some more of the little optimizations are totally things that we could do that aren't like crazy clever. He does some benchmarking. He finds like problem inputs that could cause our algorithms to look really bad, which is something to consider. Like, are we optimizing for the common case, which is what we've got with the distributed things on the random coordinates, or are we optimizing for the worst case or the best case? So he sort of does this detour where he looks at outliers and he comes up with some solutions that improve upon things. So I'm gonna commit and then push, and then let's chat for about 3 minutes and then go home. Cool. So I would like to do this class again because I think it's really interesting. But I'm disappointed that it's been like almost 2.5 hours and we didn't get super far, and I've been sort of cranking. So I was just wanted to just ask you folks for suggestions how we could do the same topic again, but with less rushedness, because I don't think it benefits anybody to rush, you or me. But maybe get further. Is there anything I could have skipped? Would it, maybe if I had the charting code, I'll put a suggestion. We could have like copied and pasted charting code
There's also iRuby notebook. Essentially, what we use,
Cool.
except for Ruby.
I'll check it out.
So you could use like the built-in graphing that he's using in his notebook.
I really like the claim about the behavior. I don't care it's in my technologies. It's cool that we generated these apps, just given their,
But Ben,
Yeah.
you found documentation saying that we can chart from this.
Yeah.
Could you tell me what to Google for?
If you go to the try.jupiter.org thing, that's kind of where they are talking about the different notebooks, and they have a small thing for Ruby. Or maybe it's on the homepage for Jupiter.org.
I can look more into it. But thanks. That sounds very cool. Other ideas if I redo this class to make it more useful?
You could share the working directory.
Oh,
Then we could just be like, we could mount that, and we could write, we could just type in Ruby run, and we can debug it with the same thing.
that's such a cool idea. Does anybody have a simple, safe way to do that?
I've been looking into bacon boxes.
Yeah, totally. I mean, that's a safe way. That's safe enough. I mean, I'm on the Noise Bridge network, so I'm already.
It's not as good as your bacon box. It's not going to be a noise bridge to get things back to you. Another idea is we could maybe, like, from this we have this commit history. And now if you go over again, you don't have to spend time typing it in class. You could be like, then we'll seek to this commit. Or you could do some weird, like, pull from a hidden repository, pull from documents and then push them or something like that. I would say on downtime.
I like these ideas because they're tech solutions. Like, it's not actually creating work for me. If I do the class once, have the deliverable that is the Git repo, and you're suggesting that I just have like an automated way to like copy a commit over one at a time. I love that because it doesn't require work from me.
Yeah, it's almost like slides in a presentation on the cover. And a repo.
And your idea for making it easy for students to screw around, that would be the ideal, is if you are screwing around and trying things or like getting ahead of me, trying different parameters and benchmarking them or writing little benchmark drivers just ad hoc or enhancing the charts like ad hoc. Well, it's really cool to have you all, the new students here. I had fun, and we should do more algorithms. Does anybody have one that you're curious about? There's so many like classics to fool around with. Oftentimes they like data structures go together with algorithms. Really nice thing about this is the data structures are super simple. So we're not like learning about graphs or other like, namely graphs or other more sophisticated data structures at the same time, which slows people down. Like I really do appreciate how Peter broke it down for us, and he doesn't assume a lot of background. Another one that would be a suggestion would be like shortest substring search. So this is like you have a big document and you want to search that document. Shortest common substring. You want to find the first interval, the instances of a substring in a large document. There's some snazzy, very clever algorithms for that. And it's just strings, right? unless you, I mean, some of them use fancy data structures, but a lot of them are just like indices where you're skipping around or populating an array. So that would be like, it's pretty sophisticated, and unlike this, it's stuff you would never have thought about. Some of the solutions, like they won like big awards back in the 70s, but you can understand the solutions, not having thought about them, and it's good practice. Cool. Well, I hope to see everybody around, and thank you.
Thank you.
Thank you.
It's great.